Today, I'd like to talk about the selective catalytic reduction of nitrogen monoxide by hydrocarbon in the presence of oxygen. This is a picture of the statue on Countdown. This is a picture of 1882. And this is a picture of 1985. You can find the change of this beautiful place to Japan. Okay. And of course, maybe you know that this terrible change is due to the acid rain or air pollution. The origin of the acid rain is mainly the nitrogen monoxide. Of course, now we have two methods to remove the nitrogen monoxide. For the industrial boiler, we are using the catalyst of vanadium, titanium, tungsten oxide by using the ammonia. But in this case, there is some problem. One problem is the leakage of dangerous ammonia. And the other one is high cost of capacity and running. For the vehicle engine, I mean the gasoline engine, we are using the so-called three-way catalyst to remove the nitrogen monoxide by hydrocarbon or carbon monoxide. However, in this case, this catalyst can be used for the diesel engine or liquid gasoline engine, because this catalyst does not work in oxygen atmosphere. As such, we have tried the ideal catalytic redox system, I mean the catalytic decomposition to yield nitrogen molecule or oxygen molecule. This is a summary of our result and the result of other workers. This is our result concerning the copper GSL5 geolite. This copper oxide is developed by Dr. Hamada of Japan National Chemical Laboratory. I don't remember the exact name of the situation, but they found that copper or sugar-promoted copper oxide is very effective for the catalytic decomposition of nitrogen monoxide. And this perovskite oxide was first developed by Professor Uchijima of Tsukuba University. This is also active at these high temperature regions. And this platinum aluminum is known as the catalyst for the decomposition catalyst. And Professor Bell is working for the detail of the reaction mechanism. In this comparison, you can find that the copper GSL5 shows the high activity at these low temperature regions. However, this catalyst has two weak points. One is for the deactivation in the presence of oxygen, and the second one is the deactivation in the presence of sulfur dioxide or water vapor. So we have tried to this selective catalytic reduction by hydrocarbon in the presence of oxygen. This is a typical result on copper GSL5 geolite. This catalyst is very active for the direct decomposition of NO. The catalytic activity to yield to nitrogen molecules is about 25% at this temperature region under these reaction conditions. However, this catalytic activity will decrease in the presence of oxygen. This result shows the pupil reduction of NO by hydrocarbon. You can find that at these high temperature regions, ammo molecule is reduced to nitrogen molecule. You can see that this red line. In this red line, the simultaneous presence of oxygen and hydrocarbon gave the nitrogen molecule nitrogen yield at this conversion level. And the reaction temperature is very low. So this result indicates there is a new catalytic reduction in the presence of oxygen. This is a summary of the effect of the hydrocarbon and carbon monoxide and hydrogen. On copper GSM5 diorite, we can use the carbon monoxide or hydrocarbon as a selective reductant. However, we can use these hydrocarbons as the selective reductant. This is the effect of the oxygen concentration. In the absence of oxygen, there is no catalytic reduction of NO to nitrogen molecule. In the presence of oxygen, there is a formation of nitrogen molecule with lone NO. At higher concentration of oxygen, the reduction of conversion to nitrogen molecule is reduced to this position. However, at this position, I mean the 10% of oxygen concentration. At this position, the oxygen concentration is 100 times larger than that of NO molecule. So I'd like to say this reaction is very selective. This arrow indicates this stoichiometric reaction. So this oxygen concentration is a very much amount of excess oxygen. This figure shows the time course of the catalytic reduction. You can find that there is no change of the catalytic activity during 30 hours. Of course, we know that this 30 hours is not sufficient for the lifetime of the catalyst. However, we don't have any automatically controlled equipment. So this 30 hours is the limit of one graduated student. Sorry. Okay, this is a brief summary of the new finding. The selective reduction of nitrogen monoxide in oxygen by hydrocarbon can be catalyzed over copper GSM5 diorite. And selective reductant is like this one, and non-selective reductant is this one. However, very recently, coral diorite is found to be active for the reduction of NO by methane. This found is recorded by AMA et al. Of Air Products, or also and Tokyo Gas Corporation. And gallium diorite is also active for the reduction of NO by methane. This is recorded by Professor Kikuchi et al. Of Waseda University. And very recently, palladium GSM5 is also active. This is recorded by Misono et al. Of the University of Tokyo. This is a summary of our recent results. And in this case, we have used the diorite material as a support. GSM5 is used. And this is the active temperature reading. And this is the activity, highly active, middle active, and low active. You can find in this position, copper or platinum is located. And cobalt or proton or silver is active at this temperature region. And at a much higher temperature region, zinc type is the active. This is a summary of the alumina catalyst. Originally, the catalytic activity of aluminum is found by Dr. Hamada result. And we have checked the effect of the addition of metal on aluminum. The catalytic activity of aluminum is increased by the addition of these metals. And the catalytic activity is not changed by the addition of these metals. And the catalytic activity of aluminum is decreased by the addition of these metals. This is a summary of the candidates for the practical catalyst, in my opinion. And copper or cobalt ion exchange GSM5 zeolite is active at this temperature region. But this catalyst is weak at water vapor or sulfur dioxide. And platinum zeolite is very active at this low temperature region. And the catalytic activity is not decreased in water or sulfur dioxide. But there is one disadvantage or byproduct of N2O. I will show you the detail in this session. And the cobalt or gallium zeolite is active for the fusion of methane. And the cobalt silver or silver chromated aluminum is active for the catalytic reduction. In this case, we can use the methanol as a selective reductant. And very recently, the platinum rhodium aluminum is reported to be active for this catalytic reduction. And I'd like to show you this platinum zeolite. The chemical condition is like this one. The concentration of MO is 1000 ppm and the HD is 1000 ppm. This figure shows the catalytic activity of precious metal loaded aluminum GSM5 zeolite. You can find that platinum, palladium, or rhodium is active. However, in this case, there is formation of large amount of nitrous oxide. This is one disadvantage of this platinum zeolite. However, the result of platinum zeolite is very similar to the present three-way catalyst. I mean, this is a report on in the SAE meeting in the United States. And this is the result of present three-way catalyst. You can find that at this low temperature region, MO is converted into mainly nitrous oxide, not N2. At higher temperature region, MO is converted to the nitrogen molecule. This result, the meaning of these results, maybe the decomposition activity for the nitrous oxide. This is the report of the arbiter of air product. They found that cobalt GSM5 zeolite or rhodium or palladium GSM5 is very active for the decomposition of H2O. However, the platinum GSM5 has a low activity for the decomposition of H2O. So there is one possibility. This is the reason for the low reactivity of H2O. However, this platinum zeolite have one disadvantage. I mean, this catalyst is very strong for the presence of water vapor. you can find that the reaction temperature is 212 degrees centigrade. There is no decrement in the presence of water vapor. The vapor pressure of water vapor is 8.6 ppm. Of course, there is some decrement of formation of N2O. But this is very strange from the other catalyst. This is an iron or copper geolite. In this case, the catalytic activity is completely destroyed. And this is the effect of the temperature in the presence or in the absence of water. You can find that there is no change of the catalytic activity to form N2. And there is a small change at this temperature region for the formation of nitrous oxide. This is one more advantage of platinum GSM5 geolite. In the absence or presence of sulfur dioxide, the catalytic activity is not so changed. Okay. At this low temperature region, the catalytic activity is slightly decreased. However, at this temperature region, there is no decrease. This is the electron microscope photograph, 10 photograph of the platinum geolite. You can find that the platinum particle on the geolite material, the distribution of the platinum is like this. So the platinum involved are the platinum particles. This is a summary of our experimental research. So this is the activity and this is the activity. In the case of selectivity, the best one is aluminum. In the activity, I mean the reaction rate, the best one is copper or copper GSM5 or platinum loaded GSM5 geolite. Of course, the target is always here. Of course, now at the present, we can find different quantities. This is a conclusion. Nitrogen monoxide can be selectively reduced by hydrocarbon in oxygen over various factors. And the presence of oxygen is essential to this selective catalytic reduction by hydrocarbon. And in the interest of time, I can talk about the detail of the reaction mechanism, but I'd like to propose this reaction mechanism. And the problem to be solved is, the first one is the enhancement of activity and selectivity. The second one is enlargement of the window, I mean the active temperature region. And the third one is the lifetime, especially durability to the water vapor, sulfur dioxide, and poison and overheating. And the last one is clarifying to the reaction mechanism. For example, quantity adjustment. Thank you very much for your attention.
Thank you very much for your very interesting presentation. Now, everybody go to the
There's been some speculation in the literature as to whether the zeolite has to have some acidity in order to be active for reduction of NO with hydrocarbons. Can you comment on that? And can you say how much acidity is present, Bronsted acidity is present for these zeolites?
I mean the effect of the geolite material on sulfur.
Right.
Yeah. We have checked the aluminum or magnesium oxide or activated carbon or other material, titanium oxide, and such material are non-sulfur for the platinum. The selectivity to to nitrogen and nitrous oxide is changed by the support. When we use the zeolite material as a support, the selectivity to nitrous oxide is the smallest one. So now we believe that the GSM5 or other zeolite material is the most suitable for the NO reduction by hydrocarbon.
The question is, why is the SM5 so different?
I don't know.
Some people have done the same thing.
That is also our question. Thank you very much.
The oxygen rule has led to the reduction of nitric oxide. My question is that have you ever tried to use the Ebert tag to identify the reduction mechanism that you propose? For instance, you can use successive injection of oxygen and hydrocarbon to see whether the oxygen promotion is like this or not.
Yes, I'm sorry, but I don't have any time to introduce the details of the reaction mechanism. Now we are reading that there are two possibilities for the reaction mechanism. The first one is concerning the oxidation of NO to NO2. Okay. We know that NO2 is a stronger oxygen than oxygen or hydrogen monoxide. So the NO2 can oxidize the hydrocarbon selectively. This is one factor. The second one is that the decomposition of NO, and the oxygen is remaining on the surface. This remaining oxygen can be swept by the hydrocarbon. This is the second one. And the third one is there is some reactive intermediate on the surface. Now we believe the third one is the correct on company in zero. However, on aluminum, I will show you. Okay, this indicates the conversion level to nitrogen molecule. And in this case, in this experiment, the oxygen concentration is always 10%. And you can compare this red line and this green line. In this case, this is the result of Hamada et al. In this case, they use the NO2 as a NOx material. And in this case, they use the NO, nitrogen monoxide. You can find that this red line is always over this green line. In this case, we can believe that oxygen molecule reacts with NO2 to form NO2. And then this NO2 oxidize hydrocarbon. As a result, NO can be reduced to nitrogen molecule. So the reaction mechanism is depending on the catalyst. I believe so.